superconductivity. Okay, thanks to organizers for inviting. It's really great to be back to Natal and to be in this wonderful institute. The title is a little bit different from what is on web. I will be talking about superconductivity inside of ferromagnet. And with this, essentially, I'm taking liberty to extend the slope of the workshop. The workshop has a title, Moray structure. This talk will be about untwisted materials like Bernal bilayer graphene, rhombohedral 3-layer, rhombohedral 5-layer graphene, which display, at least in minds of some, simultaneously ferromagnetic order and superconductivity. And there's similar phenomenon in heavy fermion materials, so I will make some reference to heavy fermion materials as well. So there are two motivations for what I'll be talking about. One motivation comes really from heavy fermion physics, and it was with us for some time, namely, why the hell it doesn't show up? Give me 1 second. I think I know what's going on. Just 1 second. Yeah, plug and plug. Yeah, let's do plug and plug. Should work now, no? Oh yes. So let's see. Yeah, now everything works. Okay, good. So for antiferromagnets, it was established long time ago, and it was a big business, to discuss how superconductivity emerges right on top of the point where, actually now I don't see anything along the axis, temperature and pressure should be here. So superconductivity emerges right at the point where antiferromagnetism starts. But if you look at ferromagnetism, situation is different, and you see mostly superconductivity inside of a ferromagnet, is uranium, germanium 2. There were reports about the same phenomenon in other systems, but they eventually didn't materialize. But still, this is a good example when superconductivity is not symmetric with respect to point where TC goes to 0. And it was under cartoons that, if you look at this in the cartoonish way, it's actually superconductivity mostly inside ferromagnetic states. So this is one motivation. Another motivation, of course, comes from the from materials which are much closer to the subject of this workshop. Number of experimental papers on bilayer, Bernal bilayer graphene, rhombohedral graphene, 4-5-layer graphene, all in a displacement field. And they show basically, you know what, I don't have to do introduction here, everyone knows what's going on. You apply displacement field, you start splitting conduction and valence band. The price you have to pay, or advantage that you get this, you get extremely flat bottom of the conduction band and flat top of the valence band, and in the presence of trigonal warping it's even more. Actually what you do, you enhance density of states in a pretty wide range of dopings, and essentially what you get in a very simple form, when you look at what happens at very small doping, you open up not exactly circular Fermi surfaces, it's more complicated, but you open up Fermi surfaces near K and K prime point. And if you don't break any symmetry, you have two degeneracies, two types of degeneracies. One obviously spin up and spin down Fermi surfaces are the same, and the second is the area of the Fermi surface near K point and near K prime point are the same, and experimentalists like to present this as 4 equal circles, which are again not exactly circles, at K and K prime, and this 4 means that there is no spin symmetry broken, no valley symmetry broken. But of course, if you look into what happens in the whole phase diagram, there is a bunch of different phases. And in these phases, which are separated with these black lines where inverse compressibility seems to diverge, there are regions which are different from this picture. Namely, you have here just one Fermi surface, you have here essentially two Fermi surfaces. Let me show the same on a larger scale. There is a range which was generally termed as half metal. Well, this picture is not entirely half metal because there are still Fermi surfaces with minority bands, but they're very small, and in some experiments there is nothing. So to first approximation, out of 4 pockets, you just have 2, and clearly you have a state in which there is just 1 pocket which is quarter metal. So half metal, quarter metal means out of 4 possible Fermi surfaces, only 2 are observed, which means 2 others are gapped, and in quarter metal is just 1. And without going into details, there was discussion going for some time, whether it's Valley polarization or spin order. And either Valley polarization or ferromagnetism by itself produces a half metal. And there is now magnetometry measurements, there are calculations in the presence of trigonal warping that seems to indicate that half metal state, at least in some substantial range of dopings and displacement field, is a ferromagnetic state. So it's a magnetic order that splits Fermi surfaces with spin up and spin down and produces a half metal. And of course, quarter metal in this regard is a state in which you have both Valley polarization and spin order. Very good. And this is the subject of half of my talk. So these regions where superconductivity has been determined are the regions which believed to be ferromagnetically ordered. I will say more about this particular region, but the whole region here is almost certainly ferromagnetically ordered region. And you see superconductivity either inside ferromagnetic state or close to the boundary of the ferromagnetic state. This number 1, and number 2, this is experiments that you all seen many times. This is from Longju group, and it tells you that if you have a quarter metal system in which you both have ferromagnetism and Valley polarization, you also have superconductivity, at least in some regions of the phase diagram where both ferromagnetism and Valley polarizations are present. So this 5-layer graphene. So now, let me say one word here. Of course, oh, by the way, this is a wonderful group of people. Interrupt me on every occasion. Really, you don't have to wait for the rest of the talk to ask questions. Just ask questions on every possibility. Yes? Yes? Yeah. Well, in heavy fermion materials, you just know where ferromagnetism is, and you know where superconductivity is. I showed you that superconducting range is inside the ferromagnetic phase. So the spin are aligned. In principle, yes. But, okay, look, in antiferromagnets, there's a whole story. There's a competition between superconductivity and antiferromagnetism. The sky, there's dome. And everything immediately dies off when you go into ordered phase. In a ferromagnet, there's a prolonged behavior, and moreover, the whole phase of superconductivity seems to be inside the ferromagnetic state. So it's not like dome on top of the critical point. It's shifted dome. This is what I was trying to say. Okay, so back to this business. Of course, superconductivity can be phonon-mediated. And we all know there's part of community on generally graphene-based systems which advocate for phonon-mediated superconductivity. But the very fact that superconductivity develops near the border of ferromagnetism makes a possibility that I'm sure will be discussed by Eris and by Paco Guinean. They did a lot of work on both ordered state and superconductivity out or close to the ordering, that superconductivity may be of electronic origin. And there is no exact proof of this, but let me take it as a working hypothesis, and I will be talking about possibility of electronic mechanism of superconductivity. And with this, let me start. And start means start with theory. And I will start with something supposedly very simple, which I thought was done years ago, but it turns out that, as the best of my knowledge and knowledge of several people who were working on the same fields, it was not done. Namely, what about superconductivity in a ferromagnetic state? This is exactly the question about competition between ferromagnetism and superconductivity. There is one extra element here which was not present in earlier works on this. There were works, of course, about superconductivity near a ferromagnetic state. Let's start with something very simple. Just one band model, forget about two valleys, forget about this model for graphene. Just the simplest possible case. We have one band model with Hubbard type interaction and single valley, and I will do even something very simple. So let's assume parabolic dispersion of fermions, a constant density of states, and let's assume that interaction is Hubbard U, but of course I want cutoff, so I just put interaction down to 0 below some cutoff. If you don't like it, use just screen Coulomb interaction, and it will do pretty much the same job. So here's what I want to do. I want to ask a question, what happens? And the first thing that special to two dimensions is how ferromagnetism develops in this model. What I will show you the results of, some call it mean field, some call it ladder approximation, but this is what happens if you do a standard Stoner theory of ferromagnetism. You find, of course, that there is a parameter, a dimensionless parameter, which is a product of interaction and the density of states. And when this dimensional parameter exceeds 1, this is where Stoner instability comes in. And what is interesting is this, that if you approach this point, everything seems to be completely normal. And in this respect, 3 dimensions and 2 dimensions don't make any difference. Have susceptibility, magnetic susceptibility, which diverges as you approach critical point. Not surprising. We expect it for any, yeah. You will see. You will see. It's an interesting situation. So on one hand, I'm talking about exactly this model within ladder approximation. Susceptibility diverges. Everyone say it should be second order phase transition. Here's how magnetization behaves. It jumps immediately from 0 to the largest possible value. So this is first order transition. This is like second order transition. Or if you like, it's first order transition without hysteresis. Without hysteresis. Just no region of hysteresis. Yeah, just to finish one phrase. So this is specific of parabolic dispersion. If you take dispersion which is not parabolic, you do have a first order transition. But first order transition such that susceptibility diverges pretty substantially. In all numerics, it diverges very strongly. And then there is a phase of first order transition. So it's not like first order transition without any hysteresis, but hysteresis region is very, very narrow. But this is most important. Yeah, Rafael. I don't think that for this calculation this matters, but all calculations are done with fixed particle number. Yeah. So this is interesting peculiarity. This is essentially what I want to do. There's also argument, old argument, and I was involved at some point with Mitty Maslov about first order transition coming from essentially dynamically generated long range interaction, but this is a minor effect compared to this one. This is a much stronger effect. So all what I want to say here, and really you do this generally by doing nothing but either ladder calculation for the order parameter or calculate free energy, zero temperature, calculate energy. Funny thing why this happens, just say one phrase, is that we normally expect that free energy of any order parameter goes as alpha eta square plus beta eta force plus etc. And this coefficient changes sign at some point. It turns out that this case, this is 0, etc. So energy, free energy or energy is just alpha eta square, eta is order parameter. So you go from behavior where as a function of eta, free energy goes like this to behavior when free energy goes like that, and there is a maximum value of eta. So it's a crazy behavior. Yeah. Yes. Yeah. Absolutely. There will be no Stoner instability. Yeah. Let me try to quickly answer, because otherwise I will not go to talk. So the story goes like this. This, what I told you, is mean field story. You start looking at corrections to mean field. There are corrections to mean field, and some of these corrections are important. And if you have large cutoff, you basically have a corrections which substantially reduce interaction U compared to what you have in mean field. And then you have no condition for Stoner instability. But the reduction depends on the cutoff. The smaller is the cutoff, the smaller is the reduction. So this is how I think you can go back to this picture. Okay, guys, at this moment, what I want to say is this. You have an ordered state in which instantly magnetization jumps to the largest value. This is a special situation, but essentially it's like first order transition. And for our perspective, what it immediately tells us that you go from full metal to half metal. Because when you have maximum magnetization, basically all fermions move from one Fermi surface to the other. You enhance by a factor of 2 chemical potential in one of the bands. Remember, density of state is a constant. But for the other band, you have a gap. And the gap is proportional to this parameter C minus 1. So you go increase C, you have gapped excitations for the down fermions. Questioner? Density of states equal to constant. Yes, but I will say even more, and then I will continue if you don't mind. So I thought that this is the reason. Well, special behavior for parabolic dispersion, density of states as a constant, you have this crazy behavior. You take dispersion k to 4th power, when density of state is not a constant. And all these coefficients again vanish. And I can show you how it happens. It's basically a question about analytic function versus expansion of analytic function versus expansion of non-analytic function. If you have any dispersion, which is in between k squared and k fourth, all those coefficients are still present. And then you have first order transition. Sign is such that you have first order transition, but you have a string between 2 points where all those coefficients vanish. And this is why the first order transition happens in the very narrow range. It's cut by both ends. Okay, yeah. Oh, I said this ladder. It's just a ladder summation. So every time when I write down an equation for the order parameter, I sum ladders of particle hole bubbles. And answering to Carlos, I've said that if you include in addition these cross diagrams, this is how you start seeing that your effective interaction changes. Yeah. Okay, let's start with this. Half metal state. We have fully saturated ferromagnetic order, and this immediately brings the system, makes the system different from what Beres and Kirkpatrick, for example, studied several years ago. Namely, there are no longitudinal excitations. It's pretty standard for people who started with helium, etc., to consider possible superconductivity due to longitudinal fluctuations of magnetic order parameter. But now we have maximum magnetization. You cannot increase it even more. So which means the residue of longitudinal susceptibility is 0. And of course it comes out as calculations. So this means interesting story is that the only excitations that you have in the system are just Goldstone modes. And so we have a situation whether there is any superconductivity mediated by Goldstone bosons. And this immediately brings memory of some people who were around 20 years ago, maybe even, well, now 25 years ago, when cuprates were discussed in this regard very extensively. So this is why I rewind clock back. Pairing in an antiferromagnet. What people discussed with respect to cuprates. And the story is there, you will see why I'm mentioning this. The story is there was, yeah, let's write down gap equations, this equation for superconducting gap, you see these two fermions have errors in the same direction, mediated by antiferromagnetic fluctuations. And apparently, and going back in time, there were papers who were saying that this is the best case for superconductivity. Apparently, what can be better than get this guys gapless? You have basically divergent susceptibility, so it's a best case scenario for pairing, apparently. But the answer is no, despite that susceptibility diverges, this static susceptibility diverges at momentum transfer equal to pi pi. In fact, if you calculate carefully vortex functions with all coherent factors included, you find that vortex functions goes to 0. And this is nothing but condensed matter reflection of what in field theory is called Adler principle, which means that if you have Goldstone bosons remain Goldstone bosons despite interaction with fermions, and if vortex would be a constant, that particle Hall bubble would immediately destroy Goldstone boson. So for antiferromagnets, the answer was, well, you multiply one by the other, you get interaction which is constant and repulsive constant. And repulsion by itself is not a big deal, because we know that repulsive interaction gives rise to D-wave attraction if it's peaked at finite momentum, but it's a constant. And therefore, there is no D-wave component. And Sushkov made an argument that on top of the constant, there is some subleading effects which still give you something, but this something is very small. Yeah? Well, if you want to do it this way, then you go beyond what I said. There is a coupling between longitudinal and transverse fluctuations, really, but I don't think that in any way destroys this argument, that there is no singular interaction that would be peaked at particular momentum. So bottom line here is that if you want to consider pairing mediated by Goldstone bosons, for antiferromagnetism, the story was don't do this. You get nothing. And in particular case here, you get again repulsive interaction. Constant means no D-wave component, so nothing. And I don't know to what extent, but still, when we look at the phase diagram of cuprates with all complications, and this is not talk about cuprates by any means, but you see superconductivity and antiferromagnetism don't mix. Neither in hole-doped cuprates, and according to all neutron studies, in electron-doped cuprates as well. So once you get superconductivity, antiferromagnetism is gone, and other way around. This was historic excurse, saying that apparently you start looking at the problem with the knowledge that probably you will get nothing. But if we have a ferromagnetic case, we have a different story. And different story comes out because of this. First of all, remember this half metal, and I put this picture just to emphasize that I will use solid line for fermions with Fermi surface and dotted line for fermions without Fermi surface. I just want to write down some diagrams. Not much. Here is what I want to say. You want to look in the interaction between low energy fermions. This is what we all want to do. Superconductivity that involves low energy fermions, because besides everything, TC is still very small. It's on the level of maximum 300 millikelvin. So this is what we want to do. Remember, these guys have Fermi surface, these guys don't have Fermi surface. So this is what we want to do. But if we look at magnon in a ferromagnet, this magnon is transverse fluctuation. So this magnon, and this is how you get it by, again, summing up, putting up transverse order parameter and summing up diagrams, ladder diagram to get susceptibility. Obviously, we get susceptibility for up-down spins, because when we take fermions with spin up and we want to excite spin wave, it also flip its spin. For antiferromagnets, this was not an issue, because for antiferromagnet, up-down spins still remain degenerate. There is no long-range order, so there's no splitting between up and down spins. But for ferromagnets, there is, and as a result, something simple happens. When you look at magnon-mediated interaction, this is what you want to get first. It's not like that. This magnon interaction acts between spin-up and spin-down spins. And as such, you can derive this interaction. Yes, this is what we did. We can derive, again, summing up this infinite series of particle Hall bubbles. We obtain effective interactions. This wavy line will mean magnon. So we get interaction, fine. But this interaction from spin up to spin down, not this one. And then, again, this is what you eventually will get spin up interaction, but not like single magnon. Single magnon will flip spin from up to down. Then you will need to go to next order, and this will be in 2 minutes. But one thing that really I thought was done 30 years ago, if not 50, but apparently it was only done last year by Zhu Dong, Jason Alicia, and Lantan Chhutibes, is that if you look at this interaction, there is no Adler principle. Namely, you write down effective interactions, this is how we derived it, mediated by magnons, and there is no zero in numerator. It's a constant. So apparently this violates Adler principle. Of course not, but it looks like this. But we know with reason. This is not a diagonal term. This is not a term which connects low energy spin excitations with low energy fermions. It's basically like going from sublattice A to sublattice B in some sense, going from ups fermions to down fermions. Very good. So this is surprisingly has not been done for years. At least I haven't seen anything like this. But this is what we need. And for this, of course, there's a next step. How to get this? Well, do it like this. Consider second order process. Second order process involves this dashed line. Remember, dashed line is down fermions. So these two are down fermions. These are gapped excitations. And as such, they don't play much role. So what's important here is just basically crossing between these two guys. And this is just nothing but convolution of two spin waves. And when you do this, of course, you find effective interaction between only up spins. If you stop here at this level, you will get singular interaction because you calculate convolution of two Goldstone bosons, and in fact, when you do this, you find singularities. But it's not the case, because in addition to single magnon process, I'm partly answering the question. In addition to single magnon process, you also have another process, direct excitement of two magnons. When you go from spin up to spin up and excite two magnons, and this is how this rectangle looks like. So again, everything is nicely comes out diagrammatically. There are more diagrams that I show, but I'm not making mistakes, so other diagrams cancel out. Very good. So what you have is another type of process, which is called in some sense first order. If you look at here, or whatever you call it, there are one vertex here, one vertex here, one vertex here, one vertex here. So altogether there are 4 vertices. I don't know how to call it. Second order, fourth order, depending on how you count number of vertices. But here there are 2. And of course, once you have this and this, you also have cross terms. When you go, obviously, 2 vertices with 1 magnon scattering and 1 vertex with 2 magnon scattering. And again, this term and these terms are different. This is really direct to magnon scattering, to magnon excitement, to magnon scattering. So you have to do a little bit work to combine all this together. And then when you combine all this together, you get effective interaction. And this effective interaction is still convolution of 2 bosonic propagators, but with some extra factor. And here is a simple result. When all momenta are 0, transferred momentum is also 0, it goes to 0. So these 4 diagrams cancel out between each other. And this Adler principle. So the fact, yeah. Yes, it remains. Let me see whether I understand the question. What happens if I rotate this and ask how fermions affect Goldstone bosons, they don't destroy a propagator of a Goldstone boson? Sorry, destroy would mean gapped. They don't gap. They're not supposed to gap. So in some sense, I'm checking that everything is fine. But to check that everything is fine, I have to do all this crazy calculations with first order, second order diagrams. Yeah, And thanks to Aries for insisting that this should be the case like this. So anyway, then you have to calculate these quantities of the same order as denominator of these two guys. And also, I didn't mention this, but if you look carefully and do careful calculations, these two guys have poles in the same half plane. So if this guy would be static, then integration over frequency would get 0. So you really need dynamical part from here to get something non-zero. Great. Before I go to result, what comes out? Let's see what we should expect and what we should look at. This is pairing. Remember, this is still story with just one piece of fermions, one Fermi surface, and we pair fermions with equal spin projection. So because we pair fermions with equal spin projection, and there's only one type of fermions, obviously gap function may be specially odd, right? That's the only possibility, standard story. So P wave, F wave, whatever. Which means that if we have interaction here, which is a constant, constant does not contribute. Constant obviously doesn't contribute to any spatially odd state. So what we do need is to look at this effective interaction and see where is a constant. And you can do this. I mean that we did this. So the largest piece in this interaction is a constant, and this constant cancels out. Or if you like, if you don't like these words, solve for the gap equation and the constant will cancel out automatically. What's important, I don't show you calculations here, just tell you what the result is. The rest is attraction. And this is something that required calculations. The rest is attraction in P-wave channel. So you can calculate dimensionless coupling constant for P-wave, and you get attractive interaction. Order, general parameter-wise, of order 1 as a function of this parameter C. Remember, C is the distance to the critical point. It goes as 1 over C. Of course, when I say it of the order of 1, I didn't mean 1 here. You need to do all full numerical calculations to get the number, and the number doesn't come out as 1. But we don't have this number at the moment exactly. So, but anyway, parameter-wise, it's all comes out as some dimensionless number in the problem, which depends on where I put cutoff for the interaction. Very good. So let's see how we are doing. Sorry. This is what I want to show, that if I do it this way, you do get superconductivity inside of ferromagnetically ordered state. And yes, it's enhanced when you approach ferromagnetic critical point, but it enhances when you approach from this side. So first quick question is, what happens on the other side? And on the other side, this is the problem that number of people sitting here approached one way or another. It's a problem about pairing mediated by small q paramagnons. It was done analytically, it was done numerically, and again, this is not a full list of people. It all started with Berg-Schrieffer with respect to helium-3, but that was 3 dimensions. In 2 dimensions, I want to play the game which I'm playing, namely parabolic dispersion. And for parabolic dispersion, you know that if you calculate this static polarization bubble just as a bubble, it doesn't depend on Q when Q is smaller than 2kF. So it's a constant. So apparently this is best case scenario. You have instability for all Q, not only for small q. Crazy scenario, but nevertheless. On the other hand, if you have Q independent interactions, there is no P wave component. So the question is who wins? Small momentum dependence of interaction, or the fact that you need momentum dependence for P wave? And I want just to emphasize to you that we of course need to deal with dynamical interaction, dynamical polarization bubble, even for free fermions, even for parabolic dispersion. It has some momentum dependence, so dynamics generate momentum dependence. So to say that polarization bubble is a constant, only true for static one. But if we expand in frequency and take only Landau damping, you get a familiar result. This is the mass, this Landau damping term. Only we used to say omega over q, more accurate formula 1 over q and square root 1 minus q over 2kf squared. And you put this into pairing, an equation for the pairing gap, and ask whether this interaction give you any component for especially odd states, p wave, f, etc. And the answer is 0. this interaction will have no zero component for any odd momentum channel. Sorry? No, it's equal spin pairing, so I cannot have it. It's equal spin pairing. Remember, I pair only spin up fermions. Oh, sorry. I gave you wrong answer. You're on the paramagnetic side. It turns out that if you look into it, the story, this formula, when you look at this guy, contains, it's a spin-mediated interaction. It's generally you look into spin singlet and spin triplet. And basically you do this very quickly. When you need to look into pairing channel, you either put I sigma y or sigma x. This is for singlet, this is for triplet. Your interaction also have sigma sigma. If you write down I sigma y with sigma sigma, you get negative sign. This means it's repulsive interaction. The only way you get something is because that's in antiferromagnetic case. Remember, this interaction was peaked at large momentum transfer, so you play a game that gap at k and gap at k plus q have opposite sign, and that's how you convert repulsion into attraction. We have here situation when momentum transfer is small. So in all even parity channel, it's just repulsive interaction. For spin triplet channel, sigma x times sigma sigma give you +1. So it's attractive interaction. Yeah, so let me hurry up because it's wonderful, but there's a second part that I want to talk about. So it's, yeah, okay, I'm going very quickly. Very good. So let me, yeah. So basically, story here is we did a little bit more accurate calculations. We added some static part, which it turns out we did some calculations with Maslov that this term exists, but when you go beyond a ladder approximation, but with very small coefficient. And long story short, we get essentially, when this coefficient is very small, we get very small superconducting TC. By the way, dots here are a result of numerical calculations. The line is analytics, which means that numerics and analytics are not bad. And there is a relation to gamma model with gamma equal to 2 here, which is all wonderful. But at the end of the day, this is what you get. You get almost nothing in a paramagnetic phase and much larger superconductivity in a ferromagnetic phase. And of course, I did separately this part and this part. If you do it more realistically, you should get something like this. And message here is that you do get superconductivity, which is peaked inside the ferromagnetic phase, but close to the boundary. And of course, I want to make connection to heavy fermion superconductors with the understanding that this is not exactly two-dimensional system, but still something comes out here. And of course, it's natural to attempt to make connection with single valley ferromagnet, which we have this quarter metal, but and it will be linked to what I'm going to talk in the next 7-8 minutes. I did calculations assuming that there is a circular Fermi surface. For circular Fermi surface, even if you have two fermions in one valley, you still get nice superconductivity. If Fermi surface is realistic, it's like this. Then k and minus k are not on the Fermi surface. And first of all, of course, in this case, when you have single valley means only here, single spin, great. If we have superconductivity here, it will be paired density wave by definition, because all fermions here are close to k point or k prime point. So in terms of counting, 2k is equal to finite number. But there's even worse here, that of course for non-circular Fermi surface, if you want to apply what I did, of course you get no Cooper logarithm. And so, which means immediately there should be threshold on the coupling. So I leave it here because there are other scenarios how to get superconductivity in this quarter metal state, and Eris will probably talk about one of them. But I want to look now, yeah. Yes. If, right.
So it's still a superconductor.
Sure. All I'm saying is that if there's not a circular form surface, if k minus k, then you don't have Cooper logarithm. Yes, absolutely. Okay, so this is what I think it's more sophisticated part of the story. Two valley. We do the same calculations, but now we have, remember, these are experiments. Now we have two valleys. And we have, in fact, three choices. Choice number one, to say, well, go back. Consider superconductivity just within one valley. This paired density wave, no difference, because I only need fermions near one valley. I can forget about other valley. But then the story about threshold on the coupling, that all comes in. But of course we have here another choice, which seemingly much better choice, because as we all know, this point k, sorry, this was paired density wave, right? This point k prime is the same as minus k. These 2 points are equivalent, so we can have fermions with k and minus k, and you can get a conventional superconductivity with zero total momentum of the pair. Great, but this is different one, because this is a pairing state that involves fermions living near k and living near k prime. And this is what you don't have when you have just one valley. And if we look here, we still have, I said altogether, three choices. So far it was 1 and 1, but this one has two choices. We want to be in a ferromagnetic state. I go back to ordered state. So we pair spins with up, and therefore we can have valley even and spatially odd states similar to what I told you before, like P wave, or we can have different situation, valley odd but spatially even. That's also a possibility. And that state, in terms of counting on special order parameters, like S wave, it has a constant gap. And because you don't need to cancel out a constant, this is much better possibility if it's realized. So let me look into this possibility, namely the state which will be odd with respect to valleys, but even with respect to momentum change. And the answer, first answer is negative. There's nothing. And the reason there's nothing, so this is what the phrase reads. If you have SU2 spin symmetry, which means that I have isotropic ferromagnet, then P wave is of course possible. It has pretty much the same story that I told you before, but potentially much stronger S wave likes is impossible because you have repulsive interaction. And the reason you have repulsive interaction is this. The game is with three types of interaction: density-density interaction within one valley, density-density interaction one valley, another valley, it's inter-valley density-density, and exchange. And when you do all calculations of the same type that I told you, isotropic two-dimensional ferromagnet, ordered state is completely spin polarized, so the same machinery as we did before, you do get attractive interactions the same way as I showed you before, but it has this wonderful ratio of this interaction and this one. And this is interaction with large momentum transfer. So if you treat all of them as screen Coulomb interactions, then of course these two are small momentum transfer, this one is large momentum transfer, so this is a small parameter. So you get attraction, but with small parameter. So you may say, so what? Well, so what? Because there is a direct interaction. Look, this is k and this is k prime. This is exactly what you have. You have two fermions with k and k prime, and they can then potentially pair. But this repulsive interaction. So this comes with minus sign. Altogether, this guy is repulsive. So you get nothing. And there is no separation of scales, nothing. It's just repulsive interaction. Very good. So apparently the result is negative, but there is some hint from experiments. And hint from experiments is that real superconductivity, which higher TC, is only obtained when BBG or RTG is placed near tungsten diselenite, and this, by all accounts, induces Ising spin-orbit coupling. And superconductivity is seen only in the range when spin-orbit coupling is substantial. And there was a statement that TC increases when spin-orbit coupling increases, which led this experimental group by Andrey Young, which involves also Nudge Perch, that superconductivity may be induced by spin-orbit coupling. Jason Alicia and other people from Caltech are on this paper. So the last thing I want to do, I want to extend all these calculations I did before to the case when we also have spin-orbit coupling, Ising spin orbit. We still get magnetism, ferromagnetism, when this parameter, you see it's now U1 plus U3, previously it was just U. This is how it works. And we still have the same situation as before, direct transition into fully polarized state. Despite that there is a spin orbit present, it's still first order transition into fully polarized half metal state. The only difference in the presence of spin orbit is that magnetization, these two values are not identical. There is of course spontaneous ferromagnetic order, this is what happens here. But there are also spin orbit induced antiferromagnetic order different in two values. Yes? No, we're talking about small filling. It's not twisted bilayer graphene. It's a situation when Fermi level is still near the bottom of the band.
Okay, so we have two bands which are spin polarized because the other two bands are way
far away. So far we're coming to this. Apparently it's observed in a ferromagnetic phase in the presence of spin orbit coupling. I will show you a picture. I will end the talk with this picture. It's just 2 or 3 more slides, no more.
So you have only one band, right?
In the ferromagnetic side, there are two values. Spin orbit coupling, right. Spin orbit coupling splits them, but you see spontaneous magnetization has much larger effect than spin orbit in this respect. Yes. Okay, maybe I can show. Do I have formulas here? No, I have theory kitchen here. So the bottom line is this. What you are saying is right, but this is a special limit. When density is so small that spin orbit is larger than density. This does not happen in experiments. We didn't consider that case. In experiment, it's still, there is no smallness. Spin orbit is of same order as interaction times density, but it's still 1/3, something like this. So it's more like ferromagnetism and some small canting that goes like this. You're talking about the case when this canting is 90 degrees. Yes. It's another way to say this. Yeah. So, theory kitchen, we do exactly the same calculations. You see, this is direct to magnon scattering. This is second order, 1 magnon scattering, cross terms here. It's, it took me some time to do this calculations. I'll put it this way. But here is this answer, that in the presence of spin orbit, we have new effect. A new effect on the first glance is completely obvious. We don't have SU2 anymore, as we have only U1, so meaning that spin orbit selects Z-axis, say spontaneous magnetization selects X-axis, goldstone is only in Y direction. There is no goldstone when we go from X to Z because of spin orbit. So as a result, if you look at spin wave spectrum is linear in momentum. At small momentum goes back to quadratic in Q at large momentum, which means this is where spin orbit is not present. And there is a parameter here. Mu naught is basically Fermi energy. So there is a parameter which contains the ratio that Adi was talking about, essentially the ratio of spin orbit and density, and the ratio of interaction. And this is generally not a small parameter. But this is a small parameter. So this beta is a small parameter in theory. And I'm saying this because then you have interesting story. You have a small frequency range where the system behavior is U1 or O2, and this is a range where system behavior is SU2 or O3, depending what you prefer. So this isotropic antiferromagnet, this is where spin orbit is relevant. And it turns out that, again, this comes out of calculations. There is attractive interaction induced by spin orbit, only existing because of spin orbit, which is attractive here and dies off in this range. Remember, previously, there was interaction that was attractive, but it was everywhere here, and it was competing with much larger repulsive interaction. So the story that I'm talking about now is that you have large repulsive interaction everywhere here, and attractive interaction which is confined to this range. In terms of formulas, I probably have no time to show this, all this, but here is the story. I just want to finish with one simple stuff. This should resemble you something. And this just what it resembles electron-phonon case in the presence of Coulomb interaction. So you remember what happens. There is a strong Coulomb interaction which acts in a wider range, and much weaker electron-phonon interaction which acts in a narrower range. And we know the result. Superconductivity does develop, but the gap has to change sign as a function of Matsubara frequency and all this beauty of, I'll call it topological superconductivity here. But bottom is that if you have a situation when there's attractive interaction in a narrow range and repulsive interaction in a much wider range, then it's a story with lambda and mu star. So then you expect that you will get superconductivity. And this superconductivity is induced by spin orbit. And the last thing is that it has some dependence of the small parameter, but also has dependence on C. And in particular, it strongly enhances again near the onset of ferromagnetism, also deep inside ferromagnetic state. But this is on the ordered state. Let me finish by showing this picture. This is canted antiferromagnet. This is superconductivity. I'm not 100% sure that this is still inside of canted phase, but it's still definitely close to the boundary. And this is what I'm referring to. And I guess with this I flash conclusions. And thanks very much.
All right. Before I pass your question, someone forgot the phone in the... And I think it's in Portuguese. We got some beads already on the dark web, but... All right, we still have time for questions. Paco?
A comment and a question.
Yeah, sure, go ahead.
First, a comment. I think what you call the valley or superconductivity, I wouldn't call it S-wave, but F-wave, because for instance, inter-valley elastic scattering will be pair-breaking.
Okay,
And
yeah.
if it is
Yes.
truly S-wave, it will not.
Yes, it's S only in the sense that, yeah, I agree with you, yes.
Now a question,
Yeah.
could you repeat, because I didn't grasp it, the hierarchy between the three U's when you have two valleys?
Yes, here it is. So this is small, this is interaction within a valley, small momentum transfer. This is interaction which at zero order is the same as U1, but when you include renormalizations beyond a ladder, they become different. This is also interaction with small momentum transfer. Momentum transfer here is the same as here. The only difference is just density of one valley times density in the other valley. And again, these two interactions are originally the same, but then when you go to renormalization, they renormalize to a different value, but still similar. This guy is interaction at large momentum transfer between one valley and other valley. And so this is normally what we neglect most of time in calculations. But for example, this interaction will distinguish between total ferromagnetism and ferromagnetism within valley and antiferromagnetism between valleys. So this is large momentum transfer interaction. And then by all accounts, it's smaller. How much smaller? Sorry? If it's attractive. If it's repulsive, I don't see immediately how you do it. Sorry? I don't think that you will see it. At least we don't see it. But let me say one phrase here. This guy and this guy participate in ferromagnetism. This is why this parameter C, which I showed, contains U1 plus U3. This guy does not participate in ferromagnetism. And so it's just like bystander in this regard. Oh, sure. Sure. If you want to go to that, But then we're talking about, yes, we are talking about order with large momentum transfer. Yeah, I'm only talking about orders with small momentum transfer. Ferromagnetism, I'm talking about ferromagnetism here. Yeah, yes, this.
I have just going back to that question that I asked at the beginning. Just to pick in my mind where you are when you're talking about the density versus the cutoff that you put on the thing. I mean, because there's a qualitative regime difference. If the interactions will be either long range or short range, and as you change the density, whatever the value of QC is, that makes a difference. So just to fix in my mind, you are in a regime, the interactions are basically considered short range in comparison to the density that you have. So the range of the interaction is short in comparison to the interparticle spacing.
Oh yes, oh yes.
At all times.
Yes.
Right?
Yes.
So that you're always safe in the sense that you don't have an evolution to a long-range regime in which the density gets so low that the range now is much
Let me put it this way. I think that, let me precisely answer to your question. Yeah. I want to answer in momentum space, but in real space. Let me try to do it.
Right.
So there is screen column interaction, and there is screening momentum. Right? Not screening length, but inverse screening length, screening momentum. I want to make the screening momentum of order of kf. Then all this works. If I want to make the screening momentum much larger than kf, on what I tell you, nothing changes. But then there is a big problem for all this business. Namely that when you want to calculate how your interaction get renormalized beyond ladder, you start seeing large corrections that reduce your interaction. You want to avoid this. Yeah.
All right, we had lots of questions during the talk, so let's thank Andrey one more time. We have a short coffee break. We'll be back at 11, okay? Half an hour from now.